So let's talk about how to blend this shape with this shape. Depending on the reference, if you only have two shapes and it's just a frame that goes by, you could just use a switch and then keyframe that switch, because again, that happens in a frame. But let's say that we have multiple sources, we need to blend this shape in multiple ways. We could rely on a blend shape SOP right here. Now for this to work, the point counts need to be the same. And so what I found works pretty well for this is if we use a poly reduce and we specify exactly how many points we want. So if we say output point counts, we can take this down to, let's say, a value of 25 as an example. And if we do that for both of these guys, so now we just have that and that. Well, let's go from that actually. We'll go maybe a value of 64 or something like that. We have 76 points, 76 points, and now we could just use this blend shape to keyframe that transformation. We will notice some artifacts. To get rid of that, use a remesh on the smaller source right here, and then we can go ahead and just change this target size until we're left with something that generally works. So I want to show you that if we had multiple shapes, we could just use this blend shape to animate this however we want. But the idea is that if we blend the shape up here, we run through everything we just did, then we should be just fine. We can cache that out and we'll have everything we need for the Axiom solver. All right, now we have this. Just a really quick source like that. Okay, let's plug this into the density and everything else we have thus far. So zooming way out here, this is my network. Don't mind this guy over here. We have the Axiom density volume, right? And we need to take that as our density. So we'll have this file SOP over here, paste relative references. That gets brought down here. And we have density, we have fuel, we have temperature. Everything we need to bring this together with the Axiom solver. Let's make the Axiom solver right here. Merge these two guys together, like so. And right now we don't have density and we don't have velocity, and those are two fields that I'll add here in a minute. But just with the density by itself and just the fuel and the temperature, what do we get when we bring this all together in the Axiom solver? Let's figure out just some base settings real quick, and from there we can add density and we can add velocity to our combustion stuff over here as well. But we have this guy, right? And the first thing that I'd like to do is notice how we have this error happening right here. That happens when this file cache errors out. And so this missing frame here, we do not want to report an error. That will cause your solver to freak out. Instead, say no geometry. And likewise for this. That should be the default for any file cache SOP that you have, because otherwise it'll freak out like you just saw. Anyway, that all goes in here. And let's say that we're on frame 30. That's going to be maybe start frame of 25 on this whole thing. So start frame of 25. The division size is fine for right now. Substeps, I always bring this to 2 substeps. Just because, especially when working with a big explosion, there's going to be values spanning quite a large distance, especially when this first blows up. And you need to have at least 2 substeps when you're trying to make something that blows up quickly like this. For the sourcing, let's go ahead and just set the density to 10 so that we can see it really well. And also, let's go to our diffusion on the temperature and turn that off. I do not want to blur temperature. I find that blurring temperature creates mushroom shapes and it also gets rid of detail. So usually you want to turn that off. Anyway, if we go forward a few frames, we end up with something like this, and we can't see it very well. So let's also set down a volume visualization, or better yet, we can do a pyro bake volume. Either one of these guys will work when trying to preview this stuff. And if we do that with the lights, we can kind of see what's going on here. So with this pyro bake volume, let's turn this up, maybe give it a sandy color that's a bit closer to what we have here on the ground. You saturate that a little bit, and there we go. Let's also go to our Axiom solver and turn on combustion. And for the fuel burn, we want this fireball to go away quickly. If this was a gasoline explosion or something where the flames last for a long time, then you want to keep that fuel burn at a lower value so that it stays there. However, in this case, we burn most of our fuel pretty much instantly. So I'll say 0.9 for that, and the fuel inefficiency at maybe about 0.1. Those guys work in general for large explosions that aren't gasoline related or aren't really any sort of source that, advects fuel all the time. So with those two guys now there, what happens when we get this? We have our dust. Looks like we are going up, but not very quickly. We do have a little bit of temperature, but we don't really get off the ground. So we need to turn up the temperature for both the sourcing and the combustion up by quite a bit. And I found that a value of around 50 seems to be appropriate for many situations. It sounds like quite a lot of temperature, but if this thing was to really blow up, it would be very hot. So these values getting high is not too bad, honestly. And notice how it sucked up all that density that we initially sourced. That really adds a lot of detail towards the bottom of this plume, which is one reason why we source density like that in the first place. But anyway, we have that, it's going up, have our little splotchy mushroom shapes. Even with just a broken up source, the shape of these mushroom clouds is much more interesting than what a default Houdini, thing would give you. So that's really cool. But where do we go from here? Well, remember back to that order of importance, how the source is the most important thing when trying to get detail. That's true in this situation. And if I'm to do a play blast of this, I want to point out something interesting about temperature and the resulting velocity that isn't so ideal. Take a look at the speed in which temperature affects velocity. What you'll notice is that it takes a little while for this thing to get going. We know that on frame 30, frame 31, that all of that temperature, all of that combustion is happening right around here, or maybe better yet around 32, 33, but we're not getting much movement from that source. And in the real world, as soon as that bomb hits, it's up in the air, it's off and running immediately. And we don't really have the time to wait for this temperature to catch up to moving this stuff around. So you might think that this is a bug or this is an error or a miscalculation by the pyro solver. You would think, okay, well, why don't we have this initial velocity going really fast? But in all reality, the pyro solver is still thinking about this properly. I mean, just imagine if you were to, let's say, take your finger and run it across a candle really fast. You wouldn't really feel much heat, right? It's only when temperature has a little bit of time to work when the full effect starts happening. And it's the same thing here. Yes, we've added a lot of temperature, but just like the candle example, you're not really going to get that velocity. You're not going to get that heat and that movement until it starts kicking in after a second or two. And so when sourcing temperature, you want to think about the temperature as the thing that drives the simulation after the initial impact. Temperature isn't really there to give you the initial impact. And if you try to overdrive temperature, you're still going to be left with this problem of not getting off the ground quickly enough. So in situations like this, we need to source in velocity directly. And not only velocity, but density as well. Because I want to make the shape that I saw in the reference. And that means having some density. That also means having some velocity that immediately pushes that shape around in the direction that I want it to go. Now, you might think, okay, well, we might be able to use pressure for that because pressure doesn't have this delayed effect. And that's kind of true, but there's a much better way of doing that. So let me show you how to create a custom velocity direction based on the shape of your source. We'll talk about how to generate that velocity field in the next video.